This lecture is a basic introduction to the Arduino programming language. This is a very optional lecture. It's really just material for brand new beginning programmers who aren't comfortable with just figuring out programming by doing, but would like a quick overview of the concepts and structure and syntax behind the Arduino programming language. So first of all, some general advice on programming guidance. There are a lot of resources that are out there to help you as an introductory programmer, including online courses. There's ones on edX and Udacity, for example. Lots of web tutorials. You might not see ones that are specific to the Arduino programming language, but if you learn to program in Java or C, that would be most appropriate. You might come across terminology about object-oriented programming. You don't need to worry about some of the more sophisticated programming constructs. You really just want to learn about basic syntax, flow, and structure of programs. There are also some Arduino-specific tutorials that you can find. There were so many that I found on the web that I couldn't find any particular one to suggest, but feel free to peruse and find one that seems useful to you and step through their programming examples. You definitely don't want to learn to program by just reading a book or reading a tutorial. You should actually be trying to implement the things that are specified in the tutorial and get some experience with debugging, because one of the most valuable skills in programming, or in life for that matter, is how to debug. How do you figure out what the error is and how to correct it? Now in this class, a few pieces of advice. One is that you will always be starting from existing programs in the Arduino programming language. These are called sketches. Each one is in a single file, and you'll be modifying them. So from the very beginning, we're going to start with an outline of a program, and there will be commented code, commented lines within that sketch, which will tell you where to put your code and what part of the code. So for example, it might say, put your haptic rendering here, and that is where you're going to describe the input-output relationships for your haptic device. Or in another location, it might say, put your force sensor calibration code here, and you should just follow those instructions. The complexity of the programming that we'll do in this class is very low. So all that you really need to get the concept of is the basic flow, structure, and syntax of a program. You don't need to think very highly about the logic of programming or doing things efficiently. The main concept in this class is just to get things working. I mentioned that debugging skills are really important, but debugging can be difficult on haptic devices, and all robot type devices for that matter, because of their real-time nature. If you're doing a typical programming assignment in a class that has nothing to do with connecting to hardware, you can kind of stop the program at any point in time and see what all the variables are and see what things are doing, and that can help you debug. The problem with both haptic interaction and robots is that you have devices that are moving in real time, and sometimes these bugs or mistakes only pop up when the system is behaving physically in the world. And it's hard to sort of stop and recreate that scenario at any time. So I do suggest that when you program, you just add one small thing at a time. Check that that thing is doing what you wanted it to, and then move on. Don't write many lines of code and then hope that it all works. Rather do lots of small checks so that overall the system maintains a behavior that you can understand. Because often, and I guarantee this will happen when you're programming haptic devices, the device will start jumping around a little bit, you'll be feeling something and going, I have no idea what that is, that's not what I programmed. But that is much less likely to happen if you program incrementally and continually test what you've added. And you should learn by doing. I always encourage the graduate students in my lab not to be afraid of breaking things. I would much rather people try things and break something than be afraid to try things. Now, the Hap Kit is not unbreakable, so I do want you to be responsible with it, because we won't necessarily be able to replace parts if you have an issue. But there's actually pretty little damage you can do to your Hap Kit through programming mistakes. One of the design features of the HapKit with the friction drive is actually so that if you've properly cut off the neoprene on the edges of the sector pulley, if the motor starts spinning uncontrollably, it'll just spin the whole sector pulley out of contact with the motor, and the motor can just spin there by itself harmlessly without really applying forces to the sector pulley or to your hand through the handle. And so in that way, we hope that the HapKit can't really be damaged by programming mistakes. Note that if your HapKit does go a little bit nuts, you can quickly remove the power to it. The first option is to remove the main power supply to the motor. The other is to also remove the USB connection because it also can get some power from the computer. I do suggest that, especially when you remove the power via the USB port, that you pull the USB out of your computer and not out of the HapKit board, because the HapKit board micro USB connector, as mentioned earlier, is somewhat delicate. But let's go on to the details of the Arduino programming language, and this lecture will be divided into three main components, talking about the structure and going over details of an Arduino programming language in terms of structural elements, variables like constants, data types, and what is the scope of a variable, and finally, functions. So going on to structure. So one of the basic things that you'll learn quickly, because you'll get all kinds of compilation errors if you don't do this, is that each statement has to end in a semicolon. So a statement is typically an assignment of a variable or a running of a function. So for example, if you want to define a variable called a as an integer and assign it to the value of 13, you have to end that line with a semicolon. Sometimes you will forget this, and the Arduino integrated development environment, when you try to compile and download your code to your HapKit board, will tell you that a semicolon is missing. But sometimes it won't quite tell you that it's missing in the place that you expect. So it can't necessarily figure out that the semicolon was supposed to be on an earlier line, and it might give you an error on a later line. So just know to look up in the code if it gives you an error that a semicolon is missing. The same thing can happen with curly braces. Curly braces, these always come in pairs. That is, every time there's an open curly brace, there has to be a matching closing curly brace somewhere else in the code. These are used to define the start and the end of functions, loops, and conditional statements. So for example, if you have a while loop, and this is one of the types of structures that we'll talk about later, you might say, while something is true, that could be a boolean expression, then you want to run all of this code here. And that code is bracketed by these curly braces. The code starts with this curly brace and it ends before the closed curly brace. And then all your statements to assign variables to values and call functions are going to go in between these curly braces. Like with the semicolon, the Arduino integrated development environment will try to help you debug if you've missed an open or closed curly brace. But again, it might not find where that error is in exactly the right place. So if it tells you a curly brace is missing on a certain line number, look above that line number if it's not absolutely clear where your curly brace is missing. Comments are extremely useful. So a single line comment is just used by a set of slashes, 2 slashes, and you can either comment out a whole line, so you could say something like this, / whole line, and then use that to describe what is going to follow in the code after that line. You can also use the single line comment in order to remove parts of your code temporarily. You don't want to do a whole lot of deleting and retyping, so it can be useful to comment something out temporarily for debugging purposes. You can also comment out just part of a line. So for example, if you have a command like the one above where we say int a equals 13, and you want to describe what a is, then you can put a comment that says a is my PIN number, and everything after the double slash is a comment, and then the part in front of the double slash is the code that will run. So these two are examples of single line comments. If you want to comment out a lot of code at once, there are buttons that you can click in the Arduino IDE that will let you add a bunch of single line comments to a bunch of lines, but then getting rid of those can be hard. So for a multi-line comment, you can put a slash and then a star, and then you can have lots of code in between, many lines with carriage returns, as long as you want, and then at the end of the comment you put another star and then a slash to end that comment. And this is a nice way to comment things out because you can do many lines at once with just a very small amount of typing. Another structure that you might want to use is a pound define. These are typically used in the beginning of a program, not inside the function. They're usually at the very top of the sketch, and they're used to give a name to a constant value, something that is never going to change again in your program. So for example, here's the code pound define LED pin 3 that might go at the top of a sketch. What this is going to do is it's going to look for these words, LED pin, as a single set of characters together, separate from any other characters, and it's just going to do a replace. If it sees LED pin, it's going to replace it with the number 3. And you can introduce bugs this way, so be a little careful. Not to also try to use this name for a variable, but it's a useful way to just assign variables that are not variables but constants that are not going to change. Now this might beg the question well, if I have a number that's not going to change, why don't I just enter 3? Why do I give it this name? So I could just enter this number instead of entering LED pin later in my code. Well, it's very useful to actually have these names. It makes your code much more readable and much more understandable, both for yourself when you're debugging, as well as other people you might share your code with. All right, arithmetic operators are a next important part of the structure. One of the most obvious things is the assignment operator. So in the assignment operator, which is just an equal sign, it simply stores the value to the right of the equal sign in the variable to the left of the equal sign. So note that whatever is on the right of the equal sign will get stored in this variable here. Now you can use this assignment operator not only to take information that you get from a function like this analog read function, but you can also use it in a variety of operations like addition, subtraction, multiplication, and division. So here are a bunch of examples where some variable called result is either an addition, subtraction, multiplication, or division of a value 1 and value 2. Later on, we'll talk about variable types. Ideally, to avoid any confusion, it's best for result, value 1, and value 2 to all be the same variable type. Like they should all be, for example, decimal integers, or they could all be floating point decimal values. So some quick tips is that you should choose variable types or sizes which are large enough to hold the largest calculated result. So for example, as I mentioned, let's say you had an integer value 1 divided by integer value 2, and the result is an integer. That might not be a great idea because if value 1 divided by value 2 it actually has a floating point value in it, then that information will get cut off in the result. So just be a little careful about your variable sizes, and I should say, and types here, sizes as well as types. And then for math, it requires fractions, as I mentioned. Using float variables is a good idea. Now, there are some drawbacks to using float variables, and we'll talk about these types a little bit more later, but namely that floating point calculations, they take a little bit more time. They also take more memory space on the HapKit board. For the size of programs that we'll be writing in this class, this is not a big deal, but if you write more complex programs, you could have a problem if you're using a lot of complicated calculations and floats where you don't need to be. In addition, you should check for order of operations. Up here we have very simple calculations, and so there's no confusion there. But let's say you have D equals A times B plus C, where A, B, C, and D are all defined variables. Well, different programming languages may handle this differently, but in Arduino, it will first multiply A and B together, and then it will do this addition step. But it's always useful just to be extra sure about what's happening to add in parentheses to help clarify which steps go together. So you might want to write it like this. Or if you purposely wanted to add B and C together before you multiplied by A, then you could write it like this. There you go. So these would give different answers, of course. Control structures are very useful parts of programs that you'll be using quite a lot. The if statement is one of the most basic. All it does is test whether a certain condition has been reached. And you can't just use an if statement by itself. It has to be if something. So it's used in conjunction with a comparison operator. So here's an example. This says if some variable is greater than 50, then you're going to do something. And that do something is whatever code you decide, whatever statements you decide to put in between these curly brackets. So this is the if statement. Note that there's no semicolon here. I shouldn't have called it an if statement. It's a control structure, not a statement. And so there's no semicolon here. The semicolons would come in the do something here statements inside the curly brackets. If else is just an expansion, lets you do more with the if statement. Basically allows you to do multiple tests. So here's an example where it says if force is greater than 1, then you do action A. Else, you do action B. And I'll just note in terms of syntax that it is okay to put the curly brackets up on this line, but I do suggest that you keep the closing curly bracket on its own, and also if you have nested statements, like if you had if force is greater than 1, and inside this action there's another if check, that you indent the new conditional statements so that you can clearly see what's going on in the code just by glancing at it. You can also do an else if statement in addition. So if you wanted to down here write else if, you could have another statement, force is less than -1, then you can have an action, and then there could still be another else statement that would happen at the end, like for action C. The for loop is another really useful control structure. It creates a loop for repetitive operations, and this is typically used to very much simplify your programming, make it efficient. So for example, here's the basic structure of a for control structure. It would say for, and then there would be an initialization code, a condition code, and an increment code. And then inside the curly braces, there would be some statements, statement or statements. So this is a nice picture of the different components from the Arduino website. So here's an example of the initialization. We declare a variable, int x equals 0. We initialize it to 0. Now you don't necessarily have to declare it as an int if your variable has already been declared, but you have to give it an initial value. So we're going to start out with x equals 0. And then there's going to be a test. You're only going to do this, this activity while x is less than 100. And then you're also going to increment x at every time through the loop. So this statement here prints a line where it just prints the value of x. And so what this will do the first time it goes through the loop is x will have a value of 0, so it would just print a 0 on the screen. The next time it comes through the loop, it would print a 1 because x++ is a sort of simplified arithmetic operator which increments x by 1. So the next time through, it will go to 1. Now, what will happen eventually is you'll get to x equals 99, and then we'll check, is x less than 100? The answer will be yes, so it will print 99, and then it will increment x by 1, and x will become 100. So the next time through the loop, it checks this test again. X is now 100, and so we do the test, is X less than 100? And the answer is no. And so then it just stops and it exits the loop. Then you're done. So because X is less than 100, you only get to 99, and then you get kicked out of the for loop. The switch case can also be useful. One example of a use of the switch case is if I've asked you to program different virtual environments like a spring and a damper and a texture, you could allow someone to change a variable value or even enter a key hit on the serial monitor in order to switch which type of virtual environment is going to be shown at a particular time. In any case, the switch statement works as follows. You switch based on a variable. So for example, your variable could be something called A, and A might have values of say 1, 2, or 3, or some other value. And what happens is there are these multiple case statements which check what A equals. So in the case that A equals 1, then you can run some code that does something when A, or in this case variable, var, equals 1. Or there's another case where this variable equals 2, and you would do something else. The default, which is optional, is to do some other code that you enter. But this is optional, so if you wanted to, you could just leave this default out. But sometimes it's nice to have a safe default in case you have some unexpected situation where that variable doesn't take on any of the values here. Now we'll talk about some comparison operators, because particularly for if statements to work, you need to have true and false statements, and that's what you get out of a comparison operator. So actually, I apologize, there is a typo here, so I'm just going to fix that. The result of a statement with a comparison operator is going to be either true, which has a value of 1, or false, which is assigned a value of 0. And here are all the comparison operators, or at least the main ones that you would want to use in Arduino code. The first one is x equals y. So this is a check. It's true if x is equal to y. This is the opposite, which is true if x is not equal to y. X is less than, greater than, less than or equal to, greater than equal to, are other examples of comparison operators. One mistake that we often see in beginning programmers is that people accidentally use the assignment operator instead of the comparison operator. So if you said something like, if x equals y, and then there was some code in here to run, what's going to happen here in this if statement is it's just going to assign x the value of y, and that value may be some number, and as long as that number is not 0, although true gets assigned a value of 1, any number that's not 0 will get interpreted as true by the Arduino compiler. So in this case, you'll always be true. So anyways, the main point is that you do not want to use the assignment operator here. You want to make sure to use the comparison operator. Also note that in an if statement, you can't use statements like, if you want x to be between 0 and 1, you can't say 0 less than x less than 1. You need to do each comparison separately. So in this case, what you would have to do is you would have to say if you wanted this to be true in order for a statement to get done, you would say if 0 is, oh sorry, I should put the x first. If x is greater than 0 and I'll talk about this and operator in I think the next slide, and x is less than 1, and I'm going to put parentheses around all of this, then I can run some statements. And so this is the way in which you need to do multiple comparisons that would replace what you would normally think of in math as a fairly simple operation. All right, so these are the Boolean operators that you can be using in order to have multiple checks in your if statement. One that you'll definitely be using in your code in this class is the logical AND, which is true only if both operands are true. So here's an example. There's two digital reads here, a digital read from pin 2 and a digital read from pin 3. And if digital read 2 is high, then everything inside the parentheses I've just drawn will just become true. It'll become a value of 1. And also, if digital read 3 is equal to high, then this will become a value of 1. And this if statement will only become true if this is 1 and this is 1. And so the stuff inside the curly braces will only get run if both inputs from the two digital read pins are high. You might also want to do an OR statement instead of an AND statement. And here's an example of this. If x is greater than 0 or y is greater than 0, then you're going to run some code. So this will happen if either x or y is greater than 0. If it was an AND statement instead of the OR statement here, then both x and y would have to be greater than 0 in order for the code between the curly braces to get run. You'll notice here that I started adding parentheses as I walk through. Partly I did this just to be clear what I was talking about when I'm pointing at things on the screen, but also it is useful programming practice, again, just to make sure that you know the order of operations that are occurring. Finally, another Boolean operator that can get used is simply true if the operand is false. So let's say you have an x variable, which is a Boolean type, which either it's true or false or 0 or 1. This checks if not x. So if x is false, not x becomes true, and then the stuff inside the if statement gets read, gets performed. So that goes over some basic structure. There are definitely other materials related to this that you can find on the Arduino website. In fact, if you go to Arduino and you look at programming language, you'll find some more detail than what I've gone over here. But let's move on to variables. So there are some basic types of variables that you need to be aware of. The first is just constants. High and low are values that are useful for defining reading or writing to a digital pin. And there's really only two possible values, high, which is a 1, or low, which is a 0. Similarly, there are also logical levels. Interestingly, the high and low are defined all uppercase, but true and false are lowercase. False is defined as 0. True is defined as 1, but more broadly, it can be anything but 0. When you are assigning a variable as true or false, if you assign it as true, it's going to become a 1. But if you're doing a check to see if some variable is true or false, if that variable is anything but 0, it's going to come back as a true. In addition, you can do constants, which are any integer or floating point values. So some examples of decimal integers are 2, 101, 3200, and some examples of floating point variables are 10.0, 2.34, and then times 10 to the 5th power, or times 10 to the minus 12th power. So if you have very large or very small numbers, you can use e, which basically is saying 10. So if I say e to the en, maybe this is equivalent to saying that that's times 10 to the n power. So because you don't want to write this number out as 234,000 necessarily, or because if it's much larger, the Arduino can't even store that number, it's useful to describe very large or very small floating point numbers with an E. Data types, which I've already mentioned in passing, are also important. Void is a very simple one. It's only used in function declarations to indicate that the function returns no information. So the two standard functions that all Arduino sketches have are the setup function and the loop function. And you'll notice that it says void in the program because the function returns no information. It does things, but it doesn't output a value at the end. However, functions that you write yourself could output a value, and we'll talk about those kinds of functions later. Another important data type is the boolean, and this is just one that holds one of two values, true or false. So an example would be you might create a boolean variable called running, assign it a value of false. You might have some other code that could potentially change if something is that variable is false or true, and then you'll have some if statement somewhere where you could say if something's running, then do something else. Other data types include character. If you want to print things to the screen through the serial monitor, for example, the character type is useful. Data type that just stores a character value. So for example, you can have a character which is the letter A, and here the A is in single quotes. You can also say that this character is equal to the number 65, and both of these examples are actually equivalent. And to see the corresponding numbers for different characters and what letters or characters they correspond to, you can look up this ASCII chart, which is pretty standard. It's not just for Arduino, it's the standard ASCII chart for used by many programming languages. But this can be used to sort of correlate numbers and characters. I mentioned already some stuff about float variables. It's the data type for floating point numbers, so it's a number that has a decimal point in it. There's also double. So floating point numbers in general are used to approximate analog and continuous values because they have greater resolution than integers. And floats have 6 to 7 decimal digits of precision. But on your HapKit board, as in most of the Arduino boards, double is actually the same as float, so it doesn't really matter if you call it double or float. It's actually going to have the same decimal digits of precision. And I realize on these slides that I think I haven't defined int, which is another important one. This is just an integer number. An integer number doesn't have any decimal points in it. It can just take on values that are integer values. It can be positive or negative or 0. Now, understanding the scope of the variable is important, especially because in haptics programming, we have a lot of variables that we want to keep track of over time. So global versus local is important to understand. A global variable is one that can be seen by every function in a program. If you want to have a global variable, the easiest thing to do is define it outside a function. So you'll actually see on your HapKit sample code that before the setup function, there are going to be a list of variables which are defined that are not inside that function. And so those are going to become global variables, and they can be seen and used by every function in the program. That is, even if there's some statements, some code in between curly braces inside of a function, it will know about those global variables. A local variable, on the other hand, is only visible to the function in which it's declared, and so you would define it inside of a function. So let's say you have a variable that you only need to use inside the loop function. Well then, after the loop function starts, you would declare that variable. You might say, for example, int a equals 2. You would put that declaration inside the loop function, and then only the loop function would know about that variable a. Now, for complex programs, the reason why you would want to have local variables is that it can help prevent programming errors. So true computer scientists are usually pretty strict about only giving variables the maximum amount of scope that they absolutely need. In this class, we're not really trying to teach you about how to do the most efficient and best kind of programs. So in terms of grading your stuff, I don't really mind if you've been a little sloppy as long as it works, but I suggest that you avoid being sloppy because then it'll make it harder to debug. Global variables are an easy way to share information across functions, and sometimes that could be required depending on what you're trying to haptically render. Now, there is a way to keep track of local variables and have them remember their value even after you've left a function. So for that, you use the static keyword. This is important because local variables typically would just get created and then destroyed every time a function is called. And yet static variables persist beyond the function call, so they preserve their data. So for example, in the loop function, the loop function gets run over and over again. It runs from top to bottom, and then it runs from top to bottom again. If you've declared a variable inside the loop function, and when you declare it, you set it to a value of 2, like this example up here, then every time you come back into the loop function again, when you do and run another instance of it, it's going to reassign that variable to 2 again. What you would rather do is assign it a static value, often, depending on what you need to do with that variable, but you might want to assign it a static value so that if something happened to that variable to change in that run through the loop function, to change that variable to a value of 3, that you would be able to remember that the next time you came into that loop function. Finally, we'll get to a description of how functions work, both functions that are provided for you with the basic Arduino programming language, as well as defining your own functions. So digital input-output is one of the most basic things you need to do, and it will help you to understand how to use the digital input-output if you look at the digital pin descriptions on the Arduino website. And these are, for the most part, the same as what you have on your HapKit board. We'll also provide a link to the details for the HapKit board pins. So in any case, the functions that you need to use in order to do digital input-output include pin mode, so you can specify a pin to behave as an input or an output. And if you look up the details of this function, you can see what you would use to replace the word mode, usually just the words input or output, and then this information here will tell you what pins are available to be in certain modes. Then you can do a digital write. You could write a high or a low value to a digital pin. Or you could do a digital read, which means you can read the value from a specified digital pin. And the result will be either high or low. And so this value is going to be high or low. The output of digital read is going to be high or low. It's not going to be any analog number, no floating point value. It's just going to be high or low. So let's look at analog input-output. For the analog systems, there is a handy function called analog reference, which can change some of the defaults about the amount of voltage and the scale at which that voltage is read or analyzed. So the default reference voltage is 5 volts, and for the purposes of this class, we're just going to leave it at that. You could change it to a different type, and so if you look up the details on the Arduino website of this function, it'll give you some different values that you could put in here, and that can change the type and function, the type and resolution using this function. You won't need to use this in this class, but if you want to do further projects with your HapKit, you might want to be changing this. The analog read function simply takes a pin on the Arduino, or in your case your HapKit board, and reads that value. It's going to assign it a value between 0 and 1023, and you should remember why this is the case from our lecture where we talked about binary numbers and analog input-output. And this will represent a voltage if you kept this default of between 0 and 5 volts. This happens actually quite quickly. It only takes 0.0001 seconds to read an analog pin. So you can actually read a lot of analog information quite quickly. Analog write is the other analog function you need to know about. This is to output information to an analog, to a pin. Now, there's not a true analog output on the Arduino or the HapKit board. And so the way it gets around this is by doing this pulse width modulation, which has been discussed in a different lecture, to a pin. So you give it a value, which is a duty cycle, between 0, which means always off, and 255, which is always on. And it works on these set of pins for the Arduino or for your HapKit board. Now, depending on exactly what kind of board you have, there may be some Arduinos which differ a little bit, but this is true for most of them. There are also some given math functions that come with the Arduino programming language which can be useful. And I'm not going to go through all of these. They're pretty self-explanatory, but you can just read them off of here. And use these so that you don't have to write your own code to figure things out. So just as an example, you could write your own code to return some value if x is less than y and a different value if y is less than x. But it can be handy to use the existing Arduino function that just outputs a value based on this minimum calculation. Serial communication functions are also really useful because it allows you to communicate between the Arduino board and the computer via the USB port. Naturally, that communication is already set up in order to download your code onto the HapKit board, but you could also in real time during your program use the serial monitor to communicate with the board. So one function that you always need to run in your setup function is the serial.begin command. You can command that this serial communications occur at a certain baud rate, which is bits per second. This is the typical one, and so this exact line here can just be placed into your code right in the setup function, and you only have to run this once to set it up for that entire sketch. I'll note that the reason why it's called a serial communication and also the serial monitor is because information that comes through a USB port is coming serially. You can imagine there being, one line of signal with information kind of coming through that line, and because it comes in one piece of information after another, it's called serial. And that's in contrast to if there were lots of pins on an interface that were coming in a parallel way. So, in case you're confused about why it's called serial, it's because it comes in an ordered information as opposed to this parallel example where the information all comes in at once on different pins. Okay, so now that you've opened up serial communications, you can do things like print to the serial monitor. And so just here's some examples of printing. You can just print directly numbers, which are integers or decimals. You can also specify the number of significant digits that are shown. So if you do a comma and then a 4, it will actually show you 4 places after the decimal point. You can also do whole strings of characters as well. If you do println instead of print, it also puts a carriage return at the end of the line. And this is useful if you're printing out data because you'd like to see the data kind of appearing like this on the serial monitor and not all run together along a single line. You can also print a value, and actually this is the println example with the carriage return. You can also do a serial read as well. So if you open up the serial monitor, you can see that there's a little window where you can type things and hit enter, and you can look up the details of the syntax for that on the Arduino website. Finally, let's talk about defining your own functions, whether you're going to make it up yourself or you're going to use a function created by other Arduino users, which, by the way, you can get at this website. Let me just show an example of a function that was defined by someone else, which is a very simple one. The idea being that although this code could just go inside of an existing function like the loop function, if you want to use it over and over again, it can be efficient to just put it somewhere else in the sketch, not inside an existing function, but by itself, typically at the end of the sketch, and then you can call it just like you would call any other of the functions that I just talked about on the last few slides. So let's quickly show this example so you can just see what it does, and you can see that it's not too complicated, but complicated enough that you might want to write a separate function for it so that you can just keep calling it instead of rewriting it over and over inside your loop function. So what this function does, it's called find text. It searches for a given string within another string. So these sort of cutely named variables are needle and a haystack. The idea is you're trying to find a needle in a haystack. So if you've defined some really complicated sentence or paragraph, which is all stored in a string, and by the way, a string is a whole set of characters, so it's another variable type we haven't talked about. So if this haystack is a bunch of characters, and you're looking for some subset of characters, the needle within that haystack, this is a function that will do so. Now, it initializes a variable called found_pos, which means did we find the position, initialize it to a value of -1. So what happens is if you don't find anything, it stays at this initialized value. So this function will return an integer value. This tells it what it will return. It's not a void here. It returns an integer of -1 if it doesn't find anything. So it returns that variable found_pos. But if it does find something, you can see that it gets changed. That variable found_pos gets changed to the value of I. And I tells you at what point in this string haystack that string called needle is found. And so there's a for loop here which initializes a variable, which is just a variable they're using for counting, I equals 0. And then they do this check. Is I less than the total length of the haystack string minus the total length of the needle string, because that's all the checks that you can do within the haystack. And then you increment I by 1 every time you go through this loop. And then it keeps checking for each value of I. If there's some substring which is equal to needle, then it makes found_pos equal to the value of I. And I is keeping track of where you are as you march through the haystack. And then it would get that value, and then it would return that value there. So a little bit of a complicated function, but something that's worth showing in terms of a good example of defining your own useful function to accomplish some task that might not come with the standard Arduino code.